In this part of the module, we will continue working with matrices. Building on what you have learned in Module 4, we will use practical examples to explore manipulating data in a matrix and using arithmetic functions with matrices. First, let's import our force plate data. Quickest way is to double-click on the data here and putting it into the workspace. Here you see it's a matrix of 200 rows by 6 columns. The first 3 columns being the x, y, and z coordinates. For the purposes of this module, we'll focus on the x, y, and z coordinates. So let's start by pulling those 3 columns out. There are 2 ways of doing this. We can pull out the x, y, and z coordinates individually and then recompose them into one file using separate commands or in one longer command. Let's first start with doing each one individually. Let's start with the x coordinate, which is column 1. So type variable. In this case, we'll say data underscore x equals data underscore 50 hertz underscore 4 seconds brackets colon comma 1, and we want to see the entire contents of this information. Do a semicolon at the end. So we're selecting all of the rows in column 1 and enter. We can do the same thing for the y coordinates or column 2. If you hit your up arrow, you will retrieve the last command you just entered, and we can edit it. And again, for z coordinate or column 3. And enter. So now we have x, y, and z, 3 sets of 200 rows as one column. This could also be useful if you wanted to manipulate the data individually for x, y, or z, or just use them as separate files. A faster way of pulling out all 3 columns into the one file would be to type data underscore xyz equals data underscore 50 hertz underscore 4 seconds, so colon, meaning all rows, in columns 1 through 3, and brackets semicolon. Now we have a file that contains x, y, and z, the first 3 columns, with 200 rows. If you want to verify that they are the same, we can open up the different files. You can see that column 1 here is the same as column 1 here and column 1 here. This being the original matrix. This is just the x we pulled out from column 1, and again this is x, y, and z, the first 3 columns combined into one larger matrix. So we can see that yes, they are all the same, so things seem to have worked properly. For this force plate data, we have the x, y, and z coordinates, but they need to be plotted against time. Since you know it's 50 hertz over 4 seconds, there's 200 rows for 4 seconds. A quick bit of math will tell you that 4 divided by 50 equals 0.02, so we have 200 increments of 0.02 to give us 4 seconds total. So how do we create a column of data that starts at 0.02, increases in increments of 0.02 up to 4? Pretty easy. Let's go t for time equals 0.02 increasing by 0.02 to 4. Since you want this to go in a column, We put a little symbol here, and again, semicolon. As you see here, we have 200 rows, 1 column. I'm going to verify that. Here we go. Up to 4. Now if we want to graph the x, y, z coordinates with time, we enter in a new variable for that, data underscore x, y, z, t equals. Since we have 2 different data sets, which we want to have organized one after the other, we can use a command called horscat, which horizontally organizes the different rows one after the other, so they don't actually overwrite one another. This command takes the 2 different sets of data and puts them one after the other, as opposed to the separate columns overlapping and one column overwriting the other. So type in HOR Z for first matrix, data underscore x, y, z, comma, your next matrix, and brackets, and again semicolon. And of course, for this to work, they have to have the same dimensions, so each column will have to have 200 rows. And enter. And here we see a matrix of 200 rows with 4 columns. We open it up and take a quick look, and x, y, and z coordinates with your time. Now that we have our data organized the way we want it, we can use different commands to actually find more information about our matrix. For instance, if you want to know the average or the mean of the x, y, z coordinates, you can type data underscore mean equals mean of data underscore x, y, z, and enter. Since we didn't use semicolon here, we got to see the results in the command window. So the average of each column, of column x, y, and z is here, but it's also here as well. If you wanted to know the mean of the rows, going horizontally, we can do that as well. Written this way, we are now taking the mean of the horizontal, so the mean of each row, and then outputting the data in one column. You can also find the sum of each column by typing data underscore sum equals sum data underscore x, y, z. Now you see the sum of each column of the x, y, and z coordinates. Now to find the sum of each row, similar to what we did in the previous example. And enter. And here you have again 200 rows, 1 column, giving the sum of each row. Another important piece of information you may be required to find is the max and min. Now to find the min of each column, it's actually pretty easy. Again, you type in data underscore min equals min data underscore x, y, z, and enter. And here you have the min with minimum for x, y, and z columns, or columns 1, 2, and 3. And to find a max is the same thing, just replace min with max. Now you have the maximum for x, y, and z, or columns 1, 2, and 3. Another useful command to not only find the max and min, but also the location, is by typing square brackets v comma l equals min data underscore xyz and enter. So again, like here, you have the min, which is 0.005, negative 1.3790, and 0.0040, but also the location. In this case, for the first column, row 53, second column, row 135, and third column, row 17. You can do the same thing for the max. Just know that when you do, you will be writing over the V and L coordinates which are located in the workspace, but you will see them here in the command window. Before we move on to using arithmetic functions with matrices, first just take a quick moment to try the do-it-yourself exercise, answer a few questions, and then move on to the next part of this module. Thank you.